Hi, welcome to this video lesson, and now in this video lesson we will discuss the rule number 2. In the previous video you must have seen the rule number 1 of data sufficiency, and here we would just like to understand that should the two statements in the data sufficiency problem be treated completely independent while we are inferring the information out of them. Then the answer to this question is yes and no both, and that's rule number 2. Now, the yes is very simple, straightforward answer, because when we deal with the two statements, then every statement must be dealt with independently unless we have already proven that the statements individually are not sufficient. Right. But the more important answer for us to understand is that why did I say no, and why should every statement not be dealt with completely independently? So this thing we will understand with the help of a few examples. So let me quickly start with a few examples. So here I am taking a quick question. Is P a prime number? If P is a prime number, what is the value of P? So now that's quite a good question, and it's categorized as the difficult question as well. Let's quickly understand how do we answer this question and what is the major learning in context of rule number 2 in this question. So let's just start simplifying this. We already know that P is a prime number. We have to find the value of P. That means we need to find the unique value of P in order to answer this question. Let's start with the first statement. The first statement says that cube root of 1 minus P square is equal to minus n, where n is a prime number. So what I'm doing is I'm taking the cube on both sides. So I get 1 minus P square is equal to minus n cube, which eventually becomes P square is equal to 1 plus n cube. Now we know that n is a prime number. So I'm going to substitute several values of n, and all of them should be the prime numbers, right? So if I take n equal to 2, then the value of P becomes square root of P square becomes equal to 9. That means P becomes plus minus 3, but since we know that P is a prime number, so we won't take any negative value. So we know that P has to be 3, which is acceptable because it's a prime number. So there is one possible value of P that we have obtained. Now, if we substitute more values of n, let's see what happens. I substitute n equal to 3, then the value of P square will be equal to 3 cube plus 1. That means the value of P will be square root of 28. And now, because value of P will be square root of 28, so certainly it's not going to be a prime number. Leave aside, it will not even be an integer. Similarly, I just want to test more such values. I am substituting n equal to 5, so the value of P becomes 5 cube 126 square root of 126, not a prime number. If you substitute n equal to 7, P is equal to square root of 344, not a prime number. Now if you see the pattern, you can understand that for every odd value of n cube will be odd, n cube plus 1 will be even. That means P will be square root of an even number, which will either not be an integer, or if it's an integer, it will certainly not be a prime number, because there is only one even prime number, that's 2. So the first statement is clearly sufficient because there is only one value of P that we have been able to obtain, and that is P equal to 3. Since we have unique value of P, therefore we say that the first statement alone is sufficient to answer the question. And right at this point, we can just quickly eliminate option B, C and E, because the answer has to be either option A or option D. Now let's quickly check the second statement. The second statement here says that 8p square plus 1 is equal to m. And now the application of the rule number 2 is going to come into the picture. Understand, here m is a prime number. Now if I want to find the values of p, what will I have to do? I will have to do p is equal to m minus 1 divided by 8 and the square root. Now we can realize that this expression is quite difficult for us to simplify. So what we can do instead is we can start substituting the value of P back here, and then we can find out the value of M. The maths is always reversible. That means if for some prime value of M, if P is going to be a prime number, the vice versa also has to be true. That means for the same prime value of P, M should also be prime number. So now what I'm going to do is I'm quickly going to substitute the values of P. But here, knowing that rule, that the first rule, the two statements cannot be in contradiction with each other, and the second statement, we can always take an inference from the first statement. Although here I am dealing with the second statement independently, but I should understand that if there is any value of p that I am going to arrive at, then it certainly has to be 3. But anyway, I'm starting with 2 because my intention is to prove that this statement is not sufficient. So if I put p equal to 2, the value of m becomes 33, which is not prime, not acceptable. If I put p equal to 3, now I know that p equal to 3 is definitely going to give me the value of m, a prime number. Only then this question will be an acceptable question for the GMAT pool. Now let's see what does m become. So p equal to 3, 3 square is 9, 9 into 8 is 72, plus 1 is equal to 73, which is a prime number. That means p equal to 3 so far is first possible value of p that's acceptable. Now we can start substituting more values of p. For example, if I put p equal to 5, which is again a prime number, then the value of m is 201, which is divisible by 3, not a prime number. If I substitute p equal to 7, then the value of m, 7 square is 49, 49 into 8 is 392 plus 1, 393, which is again not a prime number. If I substitute p equal to 11, then the value of m is 11 square is 121, 121 to 8 is 968 plus 1, 969, again a multiple of 3. Now once again you can see that there is a pattern emerging for every other prime value of p. The value of m is a multiple of 3. That means certainly it's not prime. There is only one value of p that we have got. That means the second statement alone as well is sufficient, and the answer to the question becomes option D. Now let me quickly once again emphasize why am I discussing here while I'm discussing rule number 2. The rule number 2 states, should we deal with every single statement independently? Now the answer is yes or no. Yes, we should deal with the statements independently unless we have proven that they are insufficient. But taking a certain clue from the previous statement is always helpful. In fact, a difficult statement becomes easier to interpret if we can take some inferences from the other statement, which is already easier to decipher the information from, right? So here we understood that p has to be 3, and from the first statement we took that clue that we knew that p equal to 3 has to satisfy if there is any value that's going to satisfy here. So, but we just wanted to check, because in data sufficiency we always try to find whether the statement is not sufficient or not. Our efforts are always channelized into that direction. So we did try hard, but we couldn't get any other value of p, so we said that it's sufficient to answer, and therefore the answer to the question becomes option D. Now this is one type of question that we have dealt with. So let me quickly discuss one more example so that we are certain that yes, this rule applies. So now here I am taking another question. Once again, it's a 700 difficulty level question. Let's quickly read the question first here. W, x, y, z are integers. W is greater than x, is greater than y, is greater than z, and everything is greater than 0. So they are positive essentially. The question is y a common divisor of w and x? The answer to the question needs to be given in the form of either yes or no. I hope you understand. It's type 1 question, the is type question. Now, let us see the first statement. The first statement is that w over x is equal to 1 over z plus 1 over x. We can simplify this quickly. 1 over x is equal to z plus x over zx, because we know that every variable is positive, so we can cancel them out in an equation. Now simplifying that gives me wz is equal to z plus x. Now one thing is that now I can start substituting a few values here, but this is an expression that starts getting slightly complicated. In fact, many a times a thought like this comes to my mind, that since there is no information about y, so possibly this statement is not sufficient. And considering that, I might want to move to the second statement, right? So I'm leaving the first statement right here, right? Assuming that the first statement is going to be not sufficient because I don't have any information about y, while to answer the question, I need to have some information about y. Now let's go to the second statement. The second statement, now when I simplify, I take w common, w minus y minus 2 is equal to 0, which gives me two possibilities, that either w equal to 0 or w minus y minus 2 equal to 0. But w equal to 0 is not possible because we know that w is greater than 0, which means w has to be y plus 2. Now, this is w equal to y plus 2, so there is some relationship between w and y plus 2. Now, let's quickly see. We have w here, we have y here, and we have w here, and w is equal to y plus 2. Now, between y and y plus 2, there is one more integer x, and we know that they are all integers. So, between y and y plus 2, what other integer do we know? Then the answer is there is only one integer y plus 1. So the second statement helps me understand this easily and quickly, that w and x are definitely consecutive integers, right? And the consecutive integers have highest common factor equal to 1. The greatest common factor of any two consecutive integers is 1. For example, if you say 2, 3, only 1 divides them. 3, 4, only 1 divides them. 4, 5, there is the common factor between 4 and 5 is 1. So that's how any two consecutive integers have only one common factor, and that is 1 itself. But the thing is that because z minimum has to be 1, and this means that y is greater than 1, which confirms that y can not be a factor, a common divisor of w and x both. That means the question is y a common divisor of w and x? We say the answer is definitely no. Definitely no means this statement is sufficient to answer the question. Now, but the inference from here was that w and x are consecutive integers. And now I want to just go back to the first statement and try and want to understand whether any such information can also be inferred from that relationship. So let's quickly see. Wz is equal to z plus x. Now if I want to find out several possible values of z, x and w which satisfy them, then let's see what I get. 5 into 1 is equal to 1 plus 4, 5 into 6 into 1 is equal to 1 plus 5, 7 into 1 is equal to 1 plus 6, and if I change z from 1 to the next possible value 2, then for example 8 multiplied by 2, this is 16, is equal to 2 plus 14, but that's not possible because w must be greater than x, right? So this value is not acceptable, which means raising z from 1 is not working. So by substituting values, once again we can make the inference that w and x are consecutive integers, and when they are consecutive integers, y cannot be a common divisor of w and x. That means the answer to the question using this statement as well is definitely no. That means the first statement alone as well is sufficient. So the basic strength of this explanation is that now you can see that this first statement, which was very difficult for me to interpret, with the help of second statement I was able to interpret it in slightly easier manner, and that's what is the second rule all about. That you can take a little clue from the other statement, that if any other statement is going to give me any information that cannot be out of sync, that's rule number 1, and you can always take the clue from the other statement, although you should not directly use any information of other statement into one before you have proved that the statements individually are not sufficient. I hope that makes sense and you enjoyed this explanation. Thank you so much.